Hello, my name is William Hinton, the Director of Engineering with Applied Energy based out of Michigan. As I get older, some of my perspectives have changed. I've been around this electrical business for just about 50 years, taught it at college level for almost 40, and some of my perspectives have actually changed. For example, I have figured out that whether the glass is half full or half empty, it depends if you're pouring or drinking. And as far as time, how long a minute is, depends on which side of the bathroom door you're on. I'm going to be sharing some additional perspectives that are slightly or significantly different than what you've read, what you've studied in school, what's in most of your textbooks, because we're going to look at something from a different perspective. From a power quality standpoint, the perspective of what is critical, virtually everything you use electricity for is critical. You can't do your job and earn an income, you can't buy food at the grocery store. All of those things run by electricity, as does everything in your house. Your freezer can't work. Your furnace can't work. You can't pump water out of the ground to use your well. So there's an awful lot of things, and most cars nowadays are computerized. So absolutely, it's critical. One of the main perspectives I'd like to share with you is the arrangement or interaction of voltage and current. There's a lot of instances where current is blamed and try to solve a power quality problem when in fact it's the voltage that is much more efficient to correct. So keep in mind that voltage can exist without current, but current cannot exist without voltage. Current is dependent on voltage, and one of the things that cause power quality problems, there are many power quality issues. We'll cover some of them today, but harmonics. They're multiples of the fundamental frequency, and they're harmonics of current. The current being drawn by a load is multiples of the 60 hertz, and multiples are like the second harmonic is double or 120 hertz, the third is 180, the fifth is 300, and so on. And the way that noise comes about is switch mode power supplies are switching back and forth at a particular switching frequency, and that particular frequency of switching, chopping up the voltage waveform to pull bursts of current, is what distorts the voltage waveform. Keeping in mind, for everything that happens, there is a cause. So there's cause and effect. If you're trying to solve the effect, you may be missing the actual cause. Sometimes the cause of various events are difficult to locate and solve, but if you have a fever, holding a cold rag on your forehead doesn't stop the cause of the fever. You could die trying to solve the effect of it. So another perspective. So when you have noise in your power system, many people will blame the current for the problem. Now, current is going to be drawn based on each load's impedance, the magnitude of the load or the impedance of the load. So if you have current in one part of a facility causing electrical noise that affects equipment in the other part of the facility, drawing more current when you have a current problem is not an efficient method of trying to solve that, because everything shares the same voltage. The currents are individual. For example, you have a circuit breaker that feeds one circuit, you have another circuit breaker feeds another circuit, and from your load center in your house, for example, there's many different circuits, and each circuit draws its own current. Voltage, as I've said, is common to all of the loads, and in industrial factories, a lot of sensitive equipment, the controls in the machines, the motor drives, the positioning devices or positioning drives in complicated numerical controlled equipment, they do not like the voltage instability and voltage imbalance and harmonics and other electrical noise that they're inflicted with, though they are, for the most part, the cause of this noise. So to attempt to solve some of this electrical noise, there have been various types of inductor capacitor filters called amp traps. There are other names based on brands, but they actually drain the current at the harmonic frequencies either together, which would be line to line, or all of them phase to ground to dissipate. One example of that is a 200 horsepower driven, well, the machine was an extruder for pulling material through it and holding it to size. It had a 200 horse motor. It also had a 350 kVA power filter that was trying to remove the fifth harmonic, or 300 hertz of electrical noise from the circuit. 350 kVA at 480 volts will draw approximately 400 amps of current. The voltage waveforms for this extruder are shown on this graphic here. The left-hand side was as the machine was operating. The right-hand side was with it operating with a voltage correction engaged. You'll see the voltage differential on the left side. The number in black, red, and blue are the three different phase voltages. We had from 315 to 291 volts. There was quite a difference of voltage there, quite an unbalance or imbalance. On the right, we're showing them within a volt or two. So we can see on the left graphic here the notching that was causing a significant amount of problem. It caused the motor and its drive, and in fact the power transformer feeding it, to moan and groan as the machine would physically cycle and operate. With the voltage correction on, everything operated cooler and quieter and significantly more efficient, not having to handle all of that current that was trying to get rid of the current from the electrical noise called harmonics. The power transformer itself had to power all of the load. It had to supply the power to that power filter that was being pulled to ground and dissipated as well. That's no longer a problem. The power transformer runs cool. The factory runs more efficiently, and there is much rejoicing. We can see what the actual total harmonic distortion, or the distortion for a particular harmonic, was shown on the graph on the left with the machine operating as it was, and on the right with the voltage correction engaged. And you'll see that the harmonics dropped about 38% simply by turning the disconnect on to the voltage correction system. And we've actually captured on the right hand graph what it was as we turned the disconnect on. It instantly reduced to less than approximately 1% and stayed there. One of the very serious electrical problems in virtually any facility is the significant danger to people and equipment. And that particular danger is caused by something called arc flash. And we have an entire presentation just on arc flash and how to reduce the severity and likelihood of it happening, and how it's actually can be prevented. So that will not be part of this particular presentation. However, just an overview, most of the grounds in a power system start as arcing ground faults. It's been researched since the early 1970s, and virtually all of the data concurs that it's about 80 to 85% of all the grounds start as arcing ground faults. As an arc starts, it burns the air or ionizes the air, creating a conductive path. And as the air is burning, it expands thousands of times larger, because as it gets hotter, it expands. Also, heat rises. So as the air is extremely hot, it's causing that arc to be bent up, and it can go up to arc over to ground or from phase to phase and cause a significant arc blast radius. Approximately 1 to 2 people die every day due to arc flash, and 80 more are injured. If the voltage is stabilized between the phases and ground, arc flash can be prevented at the beginning of the event. So when the phase potential is kept nominal, multiple ground faults do not cause arc flash. In many facilities and many manufacturers actually recommend adding line reactors ahead of a drive and or chokes after a drive. The chokes are there for smoothing the spindle speed, typically in a system where you would have a tool changer, and it prevents the motor from cogging or being not turning very smoothly at low speed. The line reactors are there to try to smooth the current. They don't do much for voltage, because an inductor, which is what a line reactor is, actually resists a change in current. So the change in current isn't as rapid as it would be if you just had the power feeding directly into the drive. However, to install these line reactors, you have to shut the machine off, stop it from operating, disconnect the power feed to the drive, find a place to mount these line reactors in the panel. If there isn't a spot, physically add another enclosure to house them, and then connect them in series with the power wiring feeding the drive. So though it actually does smooth the current a bit, it does have a voltage drop across it. A voltage drop in series with your drive causes the voltage to be lower at the input terminals on the drive. So that voltage can go up and down based on current, and that can cause some unrepeatability in your process. It can also cause a lower amount of torque and longer acceleration on the motor that the drive is powering. So the line reactors do not address a voltage balance. They do not address restoring the phase angle differential between phases, and there's no voltage protection from voltage spikes, and actually does minimal noise filtering. There are various power quality solutions recommended by manufacturers, some of which to smooth the current. These particular devices are for limiting voltage. The transient voltage surge suppressor is a device that uses a nonlinear component called a metal oxide varistor. As the voltage goes up, its resistance goes down. So the higher the voltage, the more current it will draw. So what they do is, as there is a voltage spike, it will convert it to a high current spike, and a spike of a couple thousand volts may be converted to 10, 20, or 50,000 amp spike in current. Every one of these spikes that it handles heats up and degrades the components in the TVSS, and many of them can take one hit. Some can take many hits below their clamping voltage, but they all help degrade. And at that point where the component fails, you no longer have protection. Many of them don't have a indication of when they failed. Some of them have a light. Some the light is on when it's good. Some the light is on when it's faulted. So there's a little confusion. And also, about half of the industrial and some commercial facilities, most chemical, virtually all offshore vessels run ungrounded power systems, either powered from an ungrounded Y generator or from delta transformers. An easy way to realize if you have that is if you have three-phase, three-wire, or a system without a neutral. TVSSs are not manufactured to protect those because they do not survive in that environment. LED lighting systems, even the lamps themselves, the light bulbs themselves, have a power supply or driver board installed in them, and they have a lot of different components. Most of them are for keeping the voltage equal and constant all of the time. They operate on direct current, so there are rectifiers to convert the AC to DC, and there are many different filters inside, as I've drawn out or shown on this slide. And the things that affect these the most are voltage. Voltage affects virtually every aspect of them. If the voltage runs higher than it should be, the lamp won't last as long. If you get a voltage spike, you can take out a portion of the array of LED lights themselves, and you will not get that 10 to 22 year projected life. The very first spike, you may see the lamp output drop by a certain percentage, 50% or 100%, based on the magnitude of the voltage spike. Here's a very good graphical representation of what a MOV-based TVSS does compared to controlling the voltage with a voltage stabilizing ground reference. On the left, we'll see a graphic that we got from the Department of Defense showing the significantly high amount of unprotected or ignored area of a voltage spike. So as the voltage gets to the switching threshold, in this case it's a 450 volt power system, so the MOV would start conducting at around 1500 volts. So there's a very small amount of protection at the top, a very large unprotected area below that. On the right, we see a stark comparison to the voltage, operating voltage envelope using a voltage stabilizing ground reference. You'll see that the voltage, entire voltage change is minimal. The voltage cannot exceed the nominal peak value. One of the significant benefits of keeping the voltages balanced is with balanced voltage you have balanced current. So here's a graph from the IEEE showing the voltage imbalance causing current imbalance. A 5% voltage imbalance can cause a 30 to 50% current imbalance in a motor. A 3% current imbalance in a motor can cause it to run excessively hot. So the voltage unbalance is a very, very critical feature, and if you have the voltage stabilized, you can prevent spikes, prevent ground faults, keep the phases 120 degrees different, phase shifted from each other, which will also help prevent arc flash. And even facilities that have relatively clean power, when they go to switch off to switch to generator, switch off to switch back to the grid, you lose your voltage and frequency reference when you are disconnected from the power source. Mother Nature causes this to happen many, many times during a storm. But the voltage and frequency does whatever it wants to as soon as the breaker opens. Spinning motors operate as generators and can typically cause the frequency to go extremely high for a second or two or five as motors are spinning down. And this can cause a lot of failures of power supplies, confused controls that will lock up and just not come back up when you reestablish power. This process of correcting the voltage waveform works in virtually any power system, from a 5-volt DC through 600-volt class equipment, residential, office, high voltage, medium voltage, power grid level. It's all directly scalable. It actually takes a very small percentage of the floor space that would be required if you're trying to clean up power by controlling or attempting to control current. The line reactors we talked about earlier, as you install them, you have to shut all of the equipment down. To install voltage correction, everything can operate, because it connects in parallel, just like another piece of equipment. It just ties into a 30 amp 3-pole disconnect, and you hook your 3 phases up and ground, and as you turn the disconnect on, your power is immediately being cleaned up. You do not have to believe power quality issues are business as usual. They now can be eliminated. When people talk about voltage spikes and arcing grounds and all of this stuff, it's just words unless you can actually see it. Here's a brief power study that was done showing many variations in the voltage. You'll see the smooth black, red, and blue lines going along. And what was going on in the middle here is there were transient voltage spikes exceeding the peak voltage significantly. They were exceeding 560 volts. There were hundreds of them over a 24 or 30-hour period. Each of them, or many of them, were causing the computer-controlled process to stop. The computer would have to be powered down and then powered back up, and the whole process restarted again. Most process control, it's very expensive every time they have to do that. You'll see on the blue phase C here, the blue one, the lines are going down, so the voltage was being pulled down towards ground. And those are called arcing ground faults. As the voltage on C was pulled down, it would cause A and B to be pulled up. So that's where we get the ragged or jagged little lines in there. Those, each of them are voltage spikes or voltage dips. And again, it was locking up the control system. On the right, we see what happens when you can stabilize and balance your voltages. You can see a couple of events that have attempted to happen. However, the arcing ground fault has been prevented. We've eliminated the arc flash hazard that could be there. And best of all of the equipment ran completely problem-free and still is to this day. A little bit about standards. The IEEE controls, regulates, and dictates to the marine industry, Coast Guard, American Bureau of Shipping, and so on, what the power systems have to be and what they have to include. They have to include insulation monitors to keep track of, is there a ground potential forming, and then when it happens, ground detection to detect that it's physically there, and something called resistance grounding to limit the amount of current if in fact the system shorts to ground. The voltage waveform correction systems provide all of these functions. In addition to that, you have local ground detection, remote ground detection, indication and alarm, as well as eliminates the presence of arcing ground faults and arc flash. So it doesn't only monitor the events, it prevents them from happening. As the IEEE discovered after 40 years of dictating the same standards, getting the same results, they were quite interested in our technology. We worked with them, and they have dictated that a voltage stabilizing ground reference is covered under their 142 grounding standard. How does this all work? Well, in application, actually applying this, you do not need to put this in at every drive or the source of each of the source of noise as you would with a TVSS. You simply have to install one per power transformer. As it hooks in parallel, it actually monitors the insulation system. It actually prevents the arcing ground faults, balances the phase voltages with respect to ground, provides a continuous 120 degree phase differential, and in a facility that there is a potential for arc flash or arcing ground faults, it actually prevents them from starting. If there is a issue, it can absorb and dissipate the actual noise energy from an event. In a three-phase 4-wire or 5-wire system, for example from a grounded Y system, you may in fact still have more harmonics at the point of common coupling that are allowed. So there's also devices that can reduce them, reduce the magnitude of harmonics, called a harmonic silencer. So and again, as the power systems get their voltage and frequency reference from the grid, adding this voltage stabilization gives you a controlled shutdown, and it prevents damage even when you lose power. The most noisy environment that there is that I've ever detected is between a variable frequency drive and its motor. It has a very high magnitude of many different harmonics. It has a significant continuous pulse train of transient voltage spikes from the output switching transistors switching on and switching off. Many of these spikes can exceed 2,000 volts, which is why the power cable between the drive and motor at 600 volt rated insulation, there's a high failure rate. It is recommended by most manufacturers now to use 1,000 volt motor power cable. The IEEE for the marine industry has indicated you need to use 2,000 volt rated insulation to prevent the breakdown of the insulation due to these voltage spikes. Also, with all of this noise, there's a 100-foot, approximate 100-foot maximum length of this power cable because of something called standing wave or reflected wave, basically the harmonics and spikes causing a problem in the wiring between the motor and drive, causing the drive itself to fault. If you can reduce the harmonics, typically by 85%, if you can eliminate the voltage spikes above the peak voltage level, then this standing wave or reflected wave is no longer a problem, and you can run as much as 1,000 feet of motor power cable between a drive and motor, allowing you to install the drive in a more convenient location rather than having to put it close to the motor. In an automotive component manufacturing facility, there was a problem where CNC machines and VFDs would fault continuously. They had a 61% imbalance in the voltages, and the drives saw that as a phase loss, not equal voltages with respect to ground. And you can see on the left side what that graphical waveform looked like. A phase was very low, B was higher than normal, and C was relatively nominal. With the voltage correction on, you'll see all three of those looked very, very clean and relatively the same as each other. Here's some additional data from that event. The power system had the three voltages we looked at in the previous slide: 123 volts for phase A, 469 for B, 360 volts for C. We see that the angle was 0, 84, and 151. They should be 120 degrees from each other. We see that graphically shown on the phase voltage imbalance, the three little arrows here, electrical vectors called phasors. And just below that, the voltage imbalance was 61%. On the bottom, we see the three significantly different impedances. What that is indicating, as the impedance becomes lower and lower, it's significantly easier for voltage to flash over. With the voltage correction on, we'll see that the phase angles here, there is 120 degrees within a couple of degrees from each other here. The voltage balance is now 6%. We'll notice that the impedances down on the bottom here are all very close to each other. And we'll notice that we have what's indicated on the left here, indication of negative resistance, is simply power being directed back into the low voltage phase, which was phase A. As you look up to phase A here, we'll see the voltages now are 257, 281, and 282. To the right of that, you'll see the three little arrows or electrical vectors called phasors. You'll see that they're virtually equal, and they have the 120 degree phase differential. And as we go to the right, you'll notice that how much energy did it take to fix that? Well, it was basically less than 1/4 of an amp. We'll see also to the right of that, all three currents are phase shifted to be 180 degrees out of phase with the phase voltage. As we remember, that's A, so the electrical vector for A is pushing to the right. The electrical vector for current is pushing to the left. We're pushing current back into phase A to push it back up to where it should be. Yeah, we've talked about volts and amps. Well, how many watts of power does this take? We'll notice here on phases B and C, it took about 38 watts of power. So this is an extremely energy efficient solution to power problems. We can see the power phasors for phase A. The wattage is shown as negative 43 watts. So you can see this is actually the power being directed back into phase A. That's why it has the negative in front of it. So it took 38 watts from B and C, and it's pushing 43 of those watts back in to phase A, pushing it back in to help balance and equalize the phase voltages. We started out talking about power quality having to do with harmonics. These are the harmonics of those events. We'll see on the left graphic a relatively high amount of third, a little bit of fifth, a little bit of 11th or 13th rather, 33rd harmonic, and this was the electrical noise in that power system. When the voltage correction was engaged, all of them were below 1%. In closing, I hope I've given you somewhat of a new perspective on what is possible. This is something that's been around for going on 18 years now. It's been extremely reliable. These particular solutions are not a one-hit wonder. They don't last just a few days, weeks, months, or years. They're designed and built to operate continuously under the most severe environments, including heavy shock and vibration, as would be on ocean-going vessels. They are outdoor or indoor rain-tight enclosures, and they should operate problem-free in a continuously grounded power system for 35 years. In normal operation, they should last well over 100. Thank you, and have a great day.